And then after I do that, I share my screen. Here, the screen that is the full screen.
Yes.
So when the students will see this screen like this.
Yes. Yes.
And then I try to go back here, and then
Yes.
I click here for.
Yeah. Thank you.
Yeah, and then you want to make sure at the end to stop recording.
Yes.
Stop sharing first and start
Stop.
recording.
Yeah. Thank you.
Yeah. Okay. Okay, everybody. I forgot to put my face shield, so now I hope you can hear me with this muffled mask. So one thing before we get started, last time we talked about potential extra credit writing a short lab report as full. I just want to make sure that it's for one short report. Short, not every potential partial turn it into full. Then the grades will be too inflated. You don't want that. Just one. If you wish to gain up to +10 points, you do it for one partial report into full. Okay? All right. So with that clear, just one last reminder. Next week, I won't be here Monday and Wednesday. I'll be thinking about you from Denmark. But you still have the lab on Monday or Wednesday. And then we have Samira lecturing on Monday, finishing up the moisture lecture, and then Sarab on Wednesday with the ash lecture. Okay, so what I'll do is I finish up UV-Vis. But the midterm, again, is up to UV-Vis. So whatever I finish today, this lecture, if I start moisture, that's not included in the midterm. Okay, just a quick recap, like always, to get us going. What is Beer's law? Elizabeth? Absolutely. It's the linear relationship between absorption and concentration, taking into account the absorptivity of each unique molecule, as well as the light path. Okay. Why absorbed light is not equal to incident minus transmitted light, Zoe?
There's also scattering methods.
Yes, scattering, reflection, potential fluorescence. So it's not equal. Okay. How does the monochromator function, Caitlin?
Basically, it bounces light and then the practice that separates the different wavelengths.
Yeah.
A specific gap that lights a particular wavelength of interest through.
Yes, absolutely. That's perfect answer. Great. Perfect and complete. I don't need to add anything. What is the importance of the monochromator in terms of Beer's law, Valerie?
It's needed for the quantification.
Yes. So can you elaborate a little bit on that? Or anyone else can elaborate? You're correct, but can you elaborate?
Yes, it because you can only have one wavelength for Beer's law.
Exactly. So for Beer's law to be obeyed, we need to have a singular wavelength because the absorptivity differs at each wavelength. So then we won't be able to follow the linear relationship of Beer's law. Great. So last time I introduced one type of UV detection using a monochromator. Now today I'm going to continue with the photodiode. The photodiode array detector, you had it in HPLC. I told you what it does, but I didn't tell you how it does it. So basically with the photodiode array detector, you get a scan of wavelength, or sorry, absorption over a wide range of wavelengths. So how does this work now when you get a spectra, fingerprint? How does it work? So the light from lamp, instead of having a monochromator here that selects one light, one wavelength to go to the sample, the entire light with all the wavelengths gets onto the sample. And your components are going to absorb light at different wavelengths. The transmitted light is going to be projected onto an array of photodiodes. That means many photodiodes. The photodiode is basically a semiconductor that converts every photon of light into an electric signal. So every wavelength with its energy is converted to electron and electric signal. That's why you see a response over the entire wavelength range, because all of the light that hits the sample and samples are going to absorb at different wavelengths. The transmitted light is going to photodiodes, that's going to, each photodiode is going to convert specific photon of light into electrical signal, and you get that spectra. Any questions on that? Yes, there. So one thing is the regular UV detector is much cheaper than this one, and you cannot produce a scan. You can only use it as one, or some UV detectors allow you to scan at 2 wavelengths. Then it will be good for quantitation, but not necessarily identification. For identification type of work, you would use a photodiode, but you can also still select one wavelength to look at the absorption at 313, for example. You can still get that lambda max absorption. Thank you. Good question. Any other? I can't breathe. Why did I do this to myself? I forgot the thing. Okay. So design of the instrument. So you can have what we call a single beam instrument or a double beam instrument. When we have a single beam instrument, you don't have a compartment for your reference or blank. You would put the blank and read the blank and zero the instrument. Then you take the blank out and put the sample in. The beam at this point will be subjected only to your place where you put your sample, blank or sample. The double beam, you have 2 places, one for the reference and one for the sample. At the same time, there are 2 places where you can put your blank and your sample. The light source gets, part of it goes to the sample and part of it splits by a mirror and goes to the reference cell. You get reading simultaneously and you get correction of the blank simultaneously. So that the read out automatically takes into account the blank reading. You don't have to manually read the blank and subtract the blank from your sample. The only disadvantage here is you're splitting your light power. You're splitting your energy power. So you have diminished radiant power, which can reduce your sensitivity, and potentially you have a higher threshold. That's the issue with a double beam. With a single beam, the issue is different. You run your blank, then you run your sample. You have to continuously, after 5 or 6 or whatever reading of sample, you have to re-zero. You have to put back the blank and adjust. Otherwise, you get deviation over time. Okay. This is FYI, nothing to memorize here, but this is to show you that different groups and example compounds These are the absorbing groups within these compounds. They have specific lambda mass, and the molecular or molar extinction is known for these compounds. So even if you don't have standards to run for calibration, if you have this information for your compound, you can actually calculate concentration, because then you have your absorptivity at a particular wavelength, you have the path length, you can relate absorption to concentration. So if your compounds of interest already have a molar extinction at a particular wavelength, you don't have to run standards. Okay, lastly here, fluorescence. The design of the fluorescence spectroscopy or spectrophotometer. What happens here is the same thing. You have the radiation source, you have wavelength isolated, either a filter or a monochromator, and you select for the lambda max where you get the maximum absorption. Then your sample is going to absorb light. Transmitted light is going to go on and continue horizontally. But the fluorescence light is directed 90 degrees into another monochromator. What happened, because the sample may fluoresce at different wavelengths. You select the wavelength at which you get the maximum fluorescence. Then you isolate that wavelength and you read the fluorescence. You have to remember when doing fluorescence, you have to select for an absorption wavelength and for a fluorescence wavelength. Which one will have higher energy? Do you remember?
The absorption.
The absorption. So which one will have lower wavelength? Absorption. So with longer wavelength, you have lower energy. So usually the absorption wavelength is a shorter wavelength, and the fluorescence wavelength is a longer wavelength. Okay, this concludes UV-Vis spectroscopy. This is where the studying ends for the midterm. Last year they had IR in the midterm. So when you look at the midterm from last year, there will be a question on IR. We didn't cover that, we ran out of time. I need to start with moisture for next week's lab. So IR will be included in a different quiz. Okay, so that's that. I'll start moisture and see how far I can get. All right, this is where the fun begins for you guys. I have to always find the best part about each section, right? So here, we start a completely new section. We're done with chromatography and spectroscopy. So now we're going to start with analysis, actual analysis. And we start with the simplest basic analysis that everybody should learn in food science, and it's proximate analysis. So in proximate analysis, what do we analyze for? You don't need to know this, we're not expecting you to know, but can you guess? Anybody want to give a go? I know, Eddie, you know. I know you're itching to tell me that you have almost all of your participation. Come on, what's under proximate analysis? What am I going to cover today? Moisture is what? Madison? Proteins, thank you. Protein lab expert. Shri? Fat, the Mojo expert. Can you? Carbohydrate, yeah, one more. Ash, perfect. You got it. All right, so proximate analysis is the measurement of main components of your food, main characters of your food. The moisture, the protein, the fat, the ash, and total carb. Now, the other piece of information that you want to know is why do we call it proximate? Not just compositional analysis or macromolecules analysis. Why do we call it approximate or proximate analysis? Okay, Abhi, tell me. Exactly, there are crude methods of analysis. Because every method, you might have other components analyzed with it. For example, when we learn protein, the main methods for proteins are based on nitrogen analysis. And nitrogen in the sample comes from other sources than the protein. You have vitamins that have nitrogen, you have uric acids that have nitrogen or urea, you have nucleic acids that might have nitrogen. So it is crude. Same with fat. You might get fat-soluble components in your fat extract that you will use to quantitate fat. So it's all crude measurements. So that's why we call them proximate analysis. Okay, so remembering nutrition label? So before I ask my question, I'm going to draw a pie chart. Okay. So all of these 5 components have to add up to 100. Because these are the main constituents within our sample. What happened? Okay, so we have moisture. What happened to Michael? Oh, okay. You have ash content. So this is ash. This is moisture. Now, depending on the sample that you have, this could be protein. This could be fat. And the rest is carbohydrate. Okay, this adds up to 100%. Perfect. So, which of these components are listed on the nutrition label? Do you find moisture content? Okay, tell me. There is no moisture or ash content. So basically, when we do proximate analysis following official methods of analysis, we get the fat, total protein, and I think fat, protein, and then total carbohydrate. These are the ones that would be listed, listed on the nutrition label. Okay. Now, this is where it gets tricky. If we want to develop our nutrition label, we have to analyze for everything. Why? Does anybody know why we have to analyze for everything to report these 3 values on the label? Alyssa? You're very right in terms of everything should add up to 100%, but true.
So you can confirm whether what you're measuring, like if you're measuring content, and then like, and you already know some of the other contents, like your ash and moisture in between, so you need to make sure it's acceptable.
You guys are thinking correctly, but what do you think?
Is it because moisture and ash can interact with the other components and affect the bioavailability of the other components?
Now we're becoming too smart for the actual answer. That's a very smart answer, but it's not the correct answer. Say that. Yeah, and what I would do is All right, because here is the answer. Total carbohydrate, there is not one official method that can give you total carbohydrate in any food. Because total carbohydrate includes starch, include dietary fiber, include resistant starch. So you do not, sugars, small molecular weight sugars. There is not one method that's going to give you total carbohydrate in a complex food matrix. You can get total carbohydrate in a beverage that only have sugars in it. Yes, you can do total carbohydrate assay, which we will learn later on. But when you have a food product that have so many different carbohydrate components, we cannot just use one method. So, because we want to have 100%, what you do is you measure moisture, ash, protein, and fat, and for the label, you subtract all of that from 100. Caitlin.
Because food labels are required to include dietary fiber and total sugars.
You do that separate.
So they would be tested separate along with everything else.
Yeah.
And it still has to add up to the total for everything you don't test.
Yes, exactly. So there is separate methods for dietary fiber that we will learn about. And there is a separate method for total sugars, mono, di, oligosaccharides. So they do that separately. But they don't have to report starch, for example. So the total carbohydrate includes sugars, dietary fiber, starch, resistant starch. So all of that. So basically, the total carbohydrate value that is reported here, we have 7 grams per serving. This came from measuring all of these 4 different components using crude methods of analysis. And then they have to all add up to 100. That's why we say 100 when it's moisture, ash, protein, and fat. So that's what you will be doing for your proximate analysis lab report. You're going to measure moisture next week. The following week, you're going to do ash and fat. The week after, you're going to do protein. You're going to write your report. You're going to determine your total carbohydrate because you have all the pieces. Okay. For addition labeling, we have to use official methods of analysis. We learned that back in chapter 3. So for moisture, we use oven drying methods. So next week, you're going to be using vacuum oven. You're going to be using forced draft oven. These both methods are official methods of analysis. You can use either to get the moisture of the product. Ash, it's always done by dry ashing because you need to get the weight of the ash. So when you put your sample, we did that for you for atomic absorption. We weighed the sample in crucible, we put it in muffled furnace, then you get everything organic will be oxidized, and then what's left is the inorganic material. And that would be your ash. So you basically weigh your sample before ashing, weigh your sample after ashing, and you get the percent ash. For ashing, for mineral analysis, you can do dry ashing, you can do wet ashing. Sharab will be talking about the difference of wet ashing versus dry ashing. But for proximate analysis, we always do dry ashing because you want to end up with ash that you can weigh and determine the percent. Fat, you're going to learn Soxhlet and Moudonier, or Mojo for short. These methods are official methods of analysis, but for the nutrition label, we don't follow either Soxhlet or Mojo. What we do is doing fatty acid analysis using the GC. So what you did in your lab, we would measure, we quantitate every fatty acid, and then we account for the weight of glycerol, and we add all of this up to get the total fat using the same method that you've done, but with calibration with standards so we can get accurate quantification. Protein, the 2 methods used for proximate, yes.
For fat analysis, I love just the 2 standard ones. Analysis.
Yes, we're going to learn, we have a whole chapter in fat analysis, but these are the ones that are most used and official methods. We have a whole chapter. Protein also, yes.
And why for fat analysis we use GC instead of the other two?
Okay, because once we learn about success and mojo, we are potentially extracting non-fat material that are soluble in the fat component. So they will be counted towards fat, but they're not. Like any soluble vitamins, fat soluble vitamins, for example, will be counted as fat. With the GC method, you're only looking at fatty acids, specifically fat content. Yeah, does that make sense? Okay. Yeah, so you're going to learn DUMAS and TELDON to do that in lab. Both are official methods of analysis, and both are based on nitrogen analysis. There are also different ways of determining protein. Also, we'll cover that in a whole class. So the carbohydrate, we have like 3 lectures on total carbohydrate because of the complexity and the different components within total carbohydrate. So that's why we don't have one assay that measures it. That's why we use the 100 minus everything else. That's the equation we use to get an approximation of the total carbohydrate. Okay. Armed with this knowledge, we can move into moisture analysis. What is true here? I see. Let's go with Caitlin. Not Caitlin. Yes, Caitlin. You're Grace. I called you Caitlin earlier. Did I say Caitlin to you? Good. I didn't.
I don't think so.
Good. I didn't. All right, Caitlin, go on. Let's see. I'm going to see what others have to say. Okay, go ahead, Dora. B and C. Dora, what did you want to do? B and C as well. Elizabeth, you have another opinion?
I was going to say none of the above.
Shri?
I was going to say just B.
Just B. Huh. And what made you just B? Who said none of the above? None of the above. Okay. So, moisture and water activity, 2 different moisture analyses, 2 different terms, they represent different things. And we're going to learn about the difference of moisture content versus water activity. But both measuring moisture content and measuring water activity lies under moisture analysis. Okay? But this is wrong. All methods for determining moisture content are based on evaporating moisture and measuring dry matter. No. You're going to learn a wonderful method in the lab next week called coefficient. It's a chemical analysis method to measure moisture content. So there are the oven methods, but there are non-oven methods, and the list is really long for moisture analysis. There will be a lot of methods we'll be introduced. Moisture content is an accurate indicator of perishability. No. Have you taken food chemistry, the water section yet? You talked about water activity being the indicator for perishability. Okay, we will talk about all of these topics as we explain methods of analysis. Your favorite topic, isotherms. It's not your favorite topic? Okay, so what is an isotherm? The relationship between moisture content and water activity used to provide information about the moisture content, water activity where you have the most stable condition. A tool that can be used to predict shelf life. Page?
All of the above.
All of the above. Okay. Yes, it is a relationship. So you have on the y-axis, you have it depends, but normally we have the water on the y-axis content, and then water activity on the x-axis. And the relationship gives you this wonderful graph we call isotherm. And there's so many different equations to determine an isotherm. Ted Lebuza's favorite topic, by the way. He retired, but he used to teach this part in this class. He won't let me teach it, basically. He's like, I'm teaching moisture now because he loves the isotherm. Okay, and then a tool that can be used to predict shelf life. Yes, we can get monolayer information, multi-layer information from that chromatogram, and we can determine where, at which point, the food is the most stable. He's back.
Yeah. He's early, finally got back.
Okay. So we say congratulations.
I've been playing phone tag with her for 2 weeks, and this is when she calls. Oh, yeah, well, she just, it was just.
Okay, we can carry this conversation. Okay, definition of moisture analysis. How do we define moisture analysis? Okay, here's a definition. Moisture analysis. It's determining water content. You can hear water content, you can hear moisture content, but that's the same thing, content, and water activity of food. You measure both characteristics, you have a complete moisture analysis. You will be doing that next week in lab. So each of you, each group will have a product, and you'll be measuring water activity and moisture content of each of these products. What is the difference between water content and water activity? Go ahead, Grace.
Water content is the total amount of water present in food. Water activity is free water versus water that's bound to other substances.
Yes, this is the most common answer. If Ted was here today, he will be not very happy, but I will take that answer as a correct answer because I'm not that picky. But here's the difference. So water content or moisture content is the total quantity of water. So everything, all the water molecules that are not bound, that are not chemically bound within a molecular structure. So anything that basically is free. Oh, you don't have that? Did you take my picture? Okay, so the dry matter that remains after water removal is referred to as total solids. So you're gonna hear these terms a lot: dry matter, total solids, total water content. Water activity, this is the correct definition that most scientific representing of water activity, although it is the free water that is not bound, is the relationship between partial pressure of water in the atmosphere above the sample. So if you have free moisture, you will have a specific water pressure above the sample. And then this is in relation to vapor pressure of pure water. So the vapor pressure of pure water is 100. So basically, whatever is the pressure of water in the atmosphere above the sample over 100 is your relative humidity. If it's out of 1, you call it water activity. If it's a percentage, you call it relative humidity. The more free water you have, the higher is your relative humidity, or the higher is the water activity. Okay. So basically, water activity of 0 is a very, very, very dry matter. You don't have any free moisture. And then water activity of 1, basically water. Okay? You have no other components that are interacting with the water. Okay. So why do we care about moisture analysis? You're gonna see me ask this question for anything now from now on. About fat, about protein, about ash, everything. Vitamins, minerals.
It affects shelf life.
Perishability, shelf life. Yes, that's one good one. What else? Hold on, let's see. You guys are all good. Anybody else would like to guess? Valerie, I'm not sure, it might be good too.
Like it would probably affect like different processes that we would put different food through.
Exactly, the moisture content determines a lot of the processing and also the transportation. Because sometimes it's harder to transport material that is high in moisture because of perishability. So oftentimes you concentrate, like you have a orange juice concentrate or milk concentrate. You have your hand up? You, Brittany.
Me? No, but I can if you want.
Okay, go ahead.
It can help determine what you can do with the food, and if you want to do like something different with that food or that component, then you need to alter it then, if that makes sense.
So processing, is that
Yeah,
what it
processing.
is? Gretchen?
It can affect the viability of pathogenic and spoilage microorganisms.
Absolutely. So this is related to perishability, but also it impacts reactions that might happen, whether it's microbial growth or chemical reactions like an enzymatic reaction, for example. Let's see what else I have here. So it is a quality factor, and also oftentimes it's part of standard of identity. For example, milk, 87% moisture. If the milk has 95% moisture, the milk is adulterated. So it's a quality check and it's standard of identity check. We talked about packaging, shipping, processing too, and then required for nutrition label. Yes, we just talked about it. We don't list it on the nutrition label, but it's required to calculate percent total carbohydrate. And oftentimes we measure moisture content specifically if we want to have our report on a dry basis. Because oftentimes if we want to compare products and we want to publish data, we need to compare based on dry matter. Because moisture content varies with under a lot of different conditions. And that brings me to why does the water moisture content varies? Moisture content varies because of the fact that the water can move from the environment to the sample and from the sample to the environment regardless of the temperature. So if there is a drop of water on this table, maybe in 15 minutes it will be dry. So we didn't reach boiling temperature, but the molecules are so active movement, they move. And that makes it really hard to handle samples for moisture quantification, actually. So that's why you're going to learn in next week that when you're preparing samples for moisture analysis, you have to avoid any conditions that can either cause the sample to gain moisture during preparation or to lose moisture during preparation. Let's say cheese. Some of you have cheese products. So when you cut the cheese and if you leave it out for a while, open in the air, and then 2 hours later you say, oh, okay, I need to weigh out my sample for moisture. Well, a lot of water dried out from the cheese. If you have baby cereal and you lay out your baby cereal, it's very dry product, but you let it sit out there exposed to the environment, it's going to capture moisture. There's always moisture vapor in the environment. It's going to capture water molecules, and then you will have an overestimation of your moisture content. And we have to always, we need to measure water in all states, which is impossible because they might lose water very quickly. You're not able to quantitate water in the gaseous state. Solid state is basically ice. So it is really hard to be able to get the accurate moisture content, and that's why it's proximate analysis of moisture. Also, you have a problem with some components that are hygroscopic. Have you heard of this term? Hygroscopic, what does it mean? Hygroscopic. Let's see. Go ahead, please.
They want to attach on the water, they want to.
Yeah, they're very hygroscopic, so they capture water in the environment. So lactose, for example, is a sugar that is very hygroscopic, so it will hold on to the water, and it's very hard to dry a product that is high in lactose. So basically, from this information, we try as best as we can to avoid moisture loss or gain during sample preparation up until measuring moisture content. Never perfect. That's why, again, it's proximate analysis. So there are many methods for measuring moisture content. Some of them are direct, especially the ovens where you put your sample, you dry the water, and then you measure the weight. And the difference is the moisture that evaporates. Rapid moisture analyzer also is based on evaporation. Thermographic analyzer, lyophilization, freeze drying, another word for it. Chemical desiccation, coefficient. We're going to talk about these in more detail. And I will probably not, I will mention indirect methods of analysis. Hydrometer is often used for very high moisture foods. Refractometer here, it's indirect because you're measuring total solids, so you can compare it to total moisture by subtracting the total solids. And IR, we didn't cover IR, but we can do moisture analysis by NIR, and so on. So there are a lot of different methods for measuring moisture content. Oven drying methods. So these are the simplest, easiest methods. If you have a vacuum oven in your lab, that's the go-to method for moisture analysis. You're going to learn vacuum oven next week. Sample is heated to evaporate the water. Very easy. You just have to take the initial weight accurately, put it in the oven for a certain period of time. Moisture evaporates, take it out, cool it down, and measure the weight. The weight difference is your moisture. So wet weight, that means the weight of your initial sample, minus dry weight. After you dry, you get a weight over the actual weight of the sample, initial weight of the sample multiplied by 100 gives you the percent moisture content. We measure moisture on dry bases. Okay, now this doesn't make sense, right? Why would you want to get moisture on dry bases? What this means is the moisture content relative to the dry matter. That's what it means for this particular measure. The relative percentage of the moisture to dry matter. So next week, I think process cheese group sample will have over 50% moisture content, over 100% moisture content on dry bases. There's nothing over 100%. Yes, in this case there is. If the moisture content is greater than the total solid content, you're going to get a percentage above 100. Because again, in your mind, it's relative. The moisture content relative to the dry matter. Why do we care? The isotherms need the moisture content on dry bases. Sometimes there's so many considerations for drying methods. Pre-drying. So food products such as milk. If you want to put milk in the forced draft oven and then boiling happens at 100 degrees, what's going to happen to the milk sample? Boil off the thing, and you would have error in measuring moisture content. So for samples such as milk, when we weigh the milk in our dish, moisture dish, we can semi-dry it a little bit in a water bath. So you put your sample above a steam or a water bath to evaporate a little bit some of the moisture, and then you put it back in the oven to avoid splattering and bubbling. Decomposition of food constituents. This is very important, guys. You will talk about it more in lab next week with Nigel and also in lecture. So chemical reactions happen if you have an oven. So if you say you have a product that has high carbohydrate, carbohydrate can burn. And when it burns, it's going to release bond water. And the release of bond water is going to cause an overestimation. So another chemical reaction can happen is Maillard reaction. You have proteins and you have reducing sugar. Maillard reaction is a condensation reaction. You lose bound water. You get overestimation of moisture. Loss of volatiles. If you have volatile like flavor compounds or any other compound that can be volatilized, it will be volatilized with the water, and then when you take the weight difference, you're going to overestimate moisture content. Last one that works in an opposite way is lipid oxidation. So you might notice that in almonds next week, the almond group. So high fat content, it can oxidize at high temperature. With oxidation, you're gaining oxygen from the environment. And the oxygen now, weight of the oxygen will be counted towards your dry matter. In this case, you get underestimation of moisture. Because now you have more dry matter, even though moisture has evaporated, you have more dry matter weight because of added oxygen, so you end up underestimating your moisture content. We need to control the temperature because you don't want high temperature because you would lose more bound water. We use specific fans. Sometimes we add covers, but in lab, for the forced draft oven, we're going to use glass wool. Forced draft is going to be forced air circulating. It's not crowded. This will probably be thrown up and we'll have Arrhenius below. So we put a piece of glass wool, or sometimes these are expensive. We use special dishes with a cover, obviously has pores so that the moisture can evaporate. Last thing, I'll let you go in 30 seconds, preventing surface crust formation. So that's why it's important to, first of all, if you have cheese, for example, you grate your cheese and you have a thin layer, you thin it out so that if it is a thick layer, you will form a crust and the moisture cannot get out of the sample. But if you have a thin layer, moisture can still evaporate. Okay, so I'll stop here and I will see you next Friday for the exam. Okay.